Thank you. Hello, hello. Perfect. I'm assuming that introduction was a nice one. My Norwegian is not great, so this is going to be in English. A few housekeeping things. First of all, I am not wearing shoes. There's a reason for this. Someone here recognized me from last year in Svalbard, the first time I presented in Norway, being the guy that put my foot on the table while I was presenting. So I figured I'd keep that trend going by not wearing shoes today. Plus, it's kind of cozy. From that experience in Svalbard, a lot has transpired, and I feel honored to have been a part of it. One of the great things is two of the students that were in Svalbard with us now work for Flir. I was lucky enough to give a reference for them. So who knows what these conferences bring. I feel like some of these things are just exposure to, the technology that I'm dealing with on a day-to-day basis. Some of it is just the networking and interactions that we have. So like I said, just who knows what comes of these sorts of things. The last thing I'd like to bring up is that if I'm assuming most people here know Anders, when Anders asks you to do something, you say, sure, I'll do that. What he wanted me to do is talk about the future of FLIR technology. Generally, manufacturers don't talk a lot about the future. We kind of keep that close and don't really provide our roadmap, but I'll give you as good of an idea of what the future should look like for us going forward. So again, my name's Randall Warnas. I've been in the industry about 6 years. Worked for DJI for a while, setting the foundation of DJI Enterprise, and then moved to Flir about 3 years ago, and have been running their global commercial payload business globally. So this is kind of, I think this is more of like a very American slide, and I actually don't really love slides like this, but you can decide whether you want to go get a coffee or something by knowing what we're going to talk about. So here we're going to talk about what thermal is, just basic, leveling of what the technology is and what it means, what resolution is with thermal imaging cameras and how that's different with between that and RGB cameras that you might be used to, different missions and the difference between qualitative and quantitative missions and how you might approach those. Emissivity, we'll talk about that in depth. I don't need to explain it now. Why you need certain pixels on your target for what you're inspecting, and just the way to think about that. The benefits of using both thermal and RGB cameras at the same time. Best practices for doing, I guess, thermal missions, specifically in mapping, and then I'll talk a little bit about the future. And a lot of this is going to be it's going to be framed in the realm of mapping. I think part of the future of thermal is going to be more orthomosaic missions, more machine vision or machine learning that's going to be able to do some autonomy on the analysis side. So that's why I'm going to be talking a little bit about mapping. We get a lot of questions about that, and so rather than just talking about strictly thermal missions like firefighting and search and rescue, I'm going to talk more about some things that you might not have heard of before. Okay, so thermal imaging, what a thermal camera does is sees the radiated energy of everything around you. So whether you're absorbing radiated energy from the sun, or you're emitting your own radiation or radiated energy through your skin that comes across as heat, the thermal camera sees in that spectrum of energy and is able to translate that into a visible image that you can understand. But aside from the, finding people in the forest type applications, you're able to also measure temperature, and you're able to do so without contact. So some of the things we talked about in Svalbard is that I work with an organization called Ocean Alliance, where they are using thermal cameras to measure the temperature of the blowhole of a whale, because they never were able to get that temperature reading before. That concept of being able to measure the temperature without actually touching something is quite compelling, and it also is used in measuring temperature of things that are extremely hot or extremely dangerous to get near, like utility lines and things like that. So I'm going to talk about, again, mapping, and I'm talking about it in the framework of two use cases. First is going to be solar. Compared to traditional inspection methods for solar farms, drone technology is said to be in between 6 and 10 times more efficient as far as the amount of time that it takes to do that complete inspection, plus it's much more accurate. So solar is one area where thermal drones are far superior than regular technology or traditional technology in doing those inspections. And these inspections are generally done in a traditional way once every 6 months or so. Where using drones, especially when regulation allows for autonomy, you could do these inspections once a week or every day. And something interesting with solar is when one cell or one panel goes out, it slowly starts to spread to the entire string. So the longer a problem exists, the more likely you're going to create a larger problem. So if you're able to respond to these issues more readily and more frequently, the longer you're going to have uptime, the more energy you're going to be getting from the panels. And then also I'm going to be talking about roof inspection. This is because there's one that's a qualitative and one that's a quantitative mission. And roof inspection not only has an efficiency factor by drones, but it's also a huge safety factor. When you have human beings walking around with handheld equipment on roofs that could be bad, could have structural issues, there's a safety factor that's involved there where they could fall through and things like that. Drones are just far superior for doing roof inspections as well. And thermal plays a big role in that. So I wanted to talk about resolution, and it's kind of a boring topic. I remember when I worked for DJI, I was sitting in a Flir conference. This is a little over 3 years ago when the Mavic 1 was released. And I remember watching the Mavic release on my laptop while I was watching thermal stuff. And I turned to my DJI colleague and I said, I'm so glad that we deal with drones and not thermal imaging because it's so boring. And now here I am speaking about thermal imaging. So I know the pain you're going through, but bear with me. Anyway, so resolution. Thermal resolution, considered high resolution, is a 640 by 512 camera. That's 640 pixels on the horizontal plane, 512 pixels on the vertical plane. So you get around 327,000 pixels. So this is very different than the megapixel concept that we get with RGB cameras. Your phone has many more pixels than a very expensive thermal imaging camera. And we'll explain why that's important. But there's also lower resolution, lower cost cameras that have become more prevalent in the market. The Mavic 2 Enterprise Dual, the Parrot and Nafi, to name a few. Those are 160 by 120 cameras, so 160 pixels horizontally, 120 vertically. So it gives you about 100, let's say, 18,000 pixels versus 327,000 pixels. So as I talk about resolution, getting pixels on target, measuring temperature, all these things should make sense of why one camera would be superior over the other. So what I did is I put a pizza pan that was about 18 inches, so translate that into meters, let's say half meter, pizza pan in the middle of the street, warmed it up just so we could get an idea of what resolution looks like at different altitudes. So this is at 25 feet or 8 meters. I did that especially for you guys, translated all of this. But basically I want to give you an idea of how this, the number of pixels becomes, it becomes a constraint as you fly higher. So at 25 feet, or 8 meters, no problem, except if you have buildings or trees or things nearby, maybe you're not able to fly at that altitude, so you have to fly higher. As we moved up, about this is 50 feet or 15 meters, you could see that still in both images, you could see the pizza pan, no problem. I roughly estimate that's the size of a person, so that you get a kind of a context of that. But you could see that there's much more detail in the 640 by 512 image, the one on the right, which the one on the left is the 160 by 120. Like I said, your Parrot and Nafis and Mavic 2 Enterprise Duals that you would get. As you move up to 100 feet, which is pretty standard for a lot of drone missions in the industrial space, you can see that the pizza pan has almost disappeared. So if, for instance, you're doing a search and rescue mission in the mountains of Norway and you wanted to find a person and you know that the trees are a little around 30 meters, so you have to fly higher than that, you're looking for a speck or a dot on the left-hand side with a 160 by 120 resolution camera. On the right-hand side is what you'd get with a 640 by 512. So the pixel count that you're getting on these cameras is extremely important when it comes to mission-critical applications. And knowing the distance that you're, the altitude or the distance from the subject you're going to be is really going to determine whether you can or cannot complete your mission. So if anyone is going to do thermal missions ever, this is like one of the most important things that I'm going to be offering you today, is this chart to tell you how high you could possibly fly to be able to see your target. In thermal, to be able to to detect something, you want to get 5 by 5 pixels on your target. So 5 pixels of the available 327,000 pixels you want to get on your target to be able to just detect it. So what we do here is and this is in inches and feet, and I apologize that I didn't translate this, but left-hand side, altitude, how high you're flying. First column is going to be 160 by 120, and the number is how many inches on the ground per pixel. So again, I didn't translate this, but let's say that we're trying to locate a cat, and that cat on the ground is 12 inches or a foot, a third of a meter. What we would do is, knowing we need 5 pixels, we would go at, if I'm looking for a 12-inch subject, divide that by 5, it's roughly 2. We would go on your chart and say, I could identify a cat or find a cat between 25 and 50 feet with a 160 by 120, or I take it to the 640 by 512 and I can see a cat at about in between 75 and 100 feet. Hopefully that makes sense, but imagine you're looking for birds, you're looking for people, you're looking for a solar cell. You can run this through the same calculation and figure out how high you can fly at a maximum to be able to identify your subject. So the difference between qualitative and quantitative missions here is whether you actually need to know the temperature of your subject. When you're doing a search and rescue mission, you don't care whether that person is 98.6 degrees Fahrenheit, whatever the body temperature is in Celsius. You don't care if they're sick. It doesn't matter. You're just trying to find the person. So that's going to be a qualitative mission where it's just, is there a difference in temperature that I can see? I don't care what the actual temperature is. It doesn't give me any useful information. Just, is there a temperature difference? Where the quantitative missions are going to be where the actual temperature of your subject matters. For instance, in utilities, the power line or the power transistors have a normal operating temperature. And so when a component falls outside of that normal operating temperature, you know there's a problem. So you need to actually measure the temperature of that component. Those are going to be quantitative missions that require radiometric cameras. So as you go into the world of thermal, you'll see a lot of cameras that are the View Pro R, Duo Pro R. The ZenMuse XT2, they're all R cameras, meaning radiometric. That means that it saves the temperature data of every pixel within the image. Maybe not super important to you now, but as you work through whether you could use thermal, you want to know whether you're doing a qualitative or a quantitative mission. One of the most important things to measuring temperature is emissivity. Emissivity is kind of the opposite of reflectivity. So when you look at a mirror or, let's say, a shiny car, you could see your reflection. So that material is going to be not very emissive. Emissivity is measured in comparison to 100% purely emissive black body. So when we look at these numbers on the right-hand side, this is, again, a percentage of a fully emissive, something that will show its temperature or the radiation coming off of it completely, rather than reflect. So different materials means the greater ability to measure that subject or that surface's temperature. So for instance, solar panels are quite uniform in their emissivity, but you do need to know the emissivity, input it into your camera so it can adjust for that reflection that comes off of the surface to be able to measure the temperature accurately. It is the most important thing to measuring temperature. The number of pixels you get on target, like I mentioned before, 5 by 5 pixels is going to be to detect. To measure temperature, you ideally want around 10 by 10 pixels. So these dots that you're seeing moving on this chart is showing the number of pixels in comparison to the accuracy of measuring temperature. This would say 10 by 10 pixels is good. I say it's good enough. But when you want true accuracy or higher accuracy, the more pixels you're getting on that subject to measure the temperature, the more likely you're going to get an accurate reading. Another important or best practice is to use both EO and IR at the same time. This means a system that has both a visible camera and a thermal camera simultaneously. Now I'm expressing this through a thing called MSX, which is when we blend those images together so that you can see here it's just thermal. When we add the MSX or the blending of the visible world on top of it, you can get more context, more information in a single image. But also most of these inspections require you to know whether that problem on your solar panel is bird poop or dirt or moisture, or if it's truly an anomaly, a crack or a broken panel. And you can only verify those things in the visible spectrum. So here are some quick best practices. Motion blur is something that exists in the visible camera as well, where if you're moving it really fast or if your subject's moving really fast, it looks blurry. The same is true with thermal imaging, so you need to make sure you're flying slow enough and high enough to make sure that you're not getting blurred images. So you can adjust those by raising your altitude, also by changing the field of view. For mapping missions, overlap and side lap is about 80%. So you're getting 80% overlap as you're flying down the rows, 80% side lap and 80% overlap. This can take a lot of time for these mapping missions. So currently mapping is not a great solution, and that's kind of why this is future thinking, is mapping will become better as battery times for drones get better, as resolution gets better, you'll be able to do more mapping missions. And then the time of day that you fly, you want to do it when delta T is the greatest. And what delta T means is the difference in temperature from your subject versus the world around it. Let's imagine I'm butt naked running around the streets of Norway right now. There's a lot of delta T between myself and the street and the environment around me, so I'm very easy to see. For solar panels, you want to fly these missions in the middle of the day when the sun is the hottest, because when you have a bad solar panel, it will show up as very hot because it's not absorbing the radiated energy, it's actually just reflecting the sun. So there's times of day that are better to fly missions than others. For roof inspection, you want to fly at the very end of the day when the moisture on the roof is holding the heat of the sun the longest. I apologize that I thought I had 20 minutes and not 15, so I'm just going to skip through this stuff fast. I'm fine? Hey, I got permission. You guys all heard that. All right, so just a few things on this. As far as the future goes, we will see software improvements and we will see machine learning. The ability to take that thermal data and just be able to alarm you when something is out of the ordinary is something, we're already there, but I think that it will just improve. It also just image assessment, being able to go through these thousands of images that drones capture and be able to determine which images might have anomalies. I think that the manual way of doing that is too time consuming, and there is a way to just have smart computers do that. So I think that's part of the future. Higher resolution, obviously. The ability to zoom thermal cameras, I think, is really important to get rid of that whole pixels on target altitude situation. But one thing that Anders wanted me to talk about is gas detection. We released the product back in September. It isn't out in the market yet because that's the problem with the drone industry and probably a problem with any manufacturers. You release things and then you find that they're not ready. But what this is a system that's only available for the Matrice 210 at the moment. It's a sniffing thing, and I'm talking about the image on the left. But what it does is it basically breathes in the air around it and can determine whether there's hazardous materials in the air. So this isn't a visual thing. This isn't like traditional thermal imaging, but it is a core competency at Flir that we have. So you're able to detect things like sulfur, carbon dioxide, and other hazardous gases that could be in the air, and that's technology that's available today. Another core competency that Flir has is optical gas imaging, which is kind of the situation on the right, where you're able to see methane and other gases that are being released largely from the oil and gas industries. That is something that we will be miniaturizing and optimizing for unmanned use. It is something that we've done for decades, and we understand it really well. But to be able to account for all of the atmospheric things and everything that's going on when flying this in the air rather than using a handheld type system from the ground, it takes a lot of time and tweaking to make sure that it's correct. But these are kind of the future things that you could expect from Flir. Like I said, the software and computer vision stuff, resolution and zoom, and then you'll see probably a lot of things in the gas space. I know that Norway specifically has a lot of access to oil and gas, and if you're part of that industry and want to be a part of potentially testing these technologies as they're available, reach out to me. That's my email. I appreciate your time, and that's it.